My name is Ron Sofferman, and I'm the CEO of RSIP Vision, and we are hosting, sponsoring this meetup. And I will tell you a little bit about our company and about other things that we do in this area of computer vision, and then we'll dive into the autonomous vehicles and more. So, a few words about RSIP Vision. RSIP Vision is a focused expert group in image processing and deep learning, and we work as a consulting and R&D group, so we work for other companies and we develop for them the modules of algorithms and AI. There are 50 engineers in our company in the Bay Area, in Boston, and also in Tel Aviv. We do most of the usual things in usual branches in computer vision, which is video processing, classification, deep learning, registration, 3D models, and inspection, and also image segmentation. As a company that works globally, we were looking for some way to contribute back to the community, and we started with a new magazine called Computer Vision News. It is dedicated for the algorithm group that is interested more in this kind of technology, not only on hardware, but specifically on software and algorithms. So the computer vision news is now very popular, and we are also the official partner of the biggest conferences in this area. So CVPR, we are doing the CVPR daily, so in case you are not going to the CVPR, you can go to our magazine and each day take a look at what is happening in this area. And ECCV, ICCV, and for the medical area, AEye. And hot from the press, the February magazine will be on autonomous driving, so you are welcome to log into our site and see the magazine. Automotive projects. We as a group that are doing many projects, we were involved in several projects in autonomous cars this year. On LiDAR, we've done a very interesting project on the LiDAR, and also analyzing the behavior of the passengers in the car, which is very important to know if everything is in place. You have the belt, and also to adjust the airbags according to whether it's adult or a child.
Can you go back to the LiDAR slide?
LiDAR?
You passed it.
Yeah, it's I'm just going not in details, just showing it. We go in details on the lectures. Also, sensor fusion. And another project that we've done is about 3D object localization. It's about tweaking the exact place of objects to enable forklifts to be very precise. So after doing all those projects, we thought this is a really good opportunity to dedicate the meeting for this area. We all know that now we are in the middle of the biggest revolution since the starting of the cars. Many of the technology of the cars were actually staying in the same place for decades. This market is very crowded. There's over 300 companies that are known. I guess that there's almost twice startups in this place. All the automakers, the technology providers, service providers, tech startups are very intensive, and more China-based companies are entering into this space, which give more activity. The commercial commercial ride-sharing services, also like Uber, is also very focusing on this area, which give us also another aspect. Large retailers such as Kroger, grocery store, and Domino's are partnering with startups to deliver groceries and other things. We all know about the levels of automation. The dream was that we will get very soon to completely automated car, but being in the last conference, actually the exhibition CES, we've seen that it's still several years ahead of us, and now we are around the 2 and 2+ area where it's only partial automation of the driver. Looking at the market trends, we see a lot of collaboration between companies that give rise to a lot of technology and a lot of power and investment from the big players and the new technologies. The market trends looks very promising. We see that in the last quarter, actually it's the second quarter, this is where it goes, this graph, the second quarter of 2018, this was the biggest investment around this area of autonomous driving. It's a very optimistic market. We can see that there are very well-funded startups with a lot of money invested in. And being at CES, we've seen that there's a lot of things that are going on. Sensor fusion becoming a standard. We see that the LiDAR prices are dropping down and getting smaller, which was one of the barriers in adopting the new technologies. AI technology becomes almost standard in the industry, which is very strong and very important for the development, because now we can see that things that haven't been driven before now coming into action. The car perception is adopted by many vendors, and we see that level 2 and top 2+ are available in the market. And also in some cases, we've been seeing that when there is some limited area, we can see that also level 4 is active when the car knows exactly what is the environment that it's expecting. Full level 5 will take a few years, and we still have a long way to do. So today we have a very interesting lecturer, and we'll start with Abhijit Thatte from AEye, and he will tell us about the new development in this company. So please welcome Abhijit.
Everything that's being trained is being trained on VGA, for example, so we could do the same thing with other variables. It all depends, really. Yes? We don't. Everything we do is from 2D. We don't. Everything I mentioned is 2D based only. We have to keep it cheap and reasonable, and you'd be surprised what you can do with 2D today. Now, having said that, we are a multi-camera system. So if we put 2 cameras on the A pillars, you can easily, not easily, but you could draw some sort of depth information. You could go all the way to reconstructing what the scene is. Per camera. There may be some image stitching, but everything so far is per camera. There may be some different requirements from customers later on, but you have to keep it modular too, right? At first. Once you're confident every camera is doing the right thing, looking at the right zone, etc., it's easy actually to stitch, or it's easy to take inputs from 2 cameras at the same time. Yes?
Do you provide the same quantity of information at night?
So, half of the driving happens at night. Therefore, I mentioned earlier with 2D camera agnostic, that includes IR or near IR. It's actually all near IR because the wavelength for automotive grade is 940. So we don't sell cameras, we don't provide cameras, we provide software and a chip. Customer works on their own cameras, they're cheap, they like to make a margin there anyways, it's a hardware, we don't need to keep inventory, it's a whole lot of hassle. They can add LEDs to their cameras. There's some new things actually that are not just LEDs, like glass fibers, I don't know if you've heard of them. I don't know if you've seen those ambient lights in Mercedes, and, right, by the doors and through the dashboard. So you can think of the same thing that's doing actually infrared, invisible. It's actually hidden, you don't see it, you don't ever see it. And it bathes the entire cabin unanimously with the right amount of light, or IR, automotive grade IR, 940 nanometers, as needed, because there's light sensors, right? What's important is that we require their cameras to be sensitive to low light conditions, or work well under low light conditions. There are typically 3 camera sensors, and so a lot of people choose Sony over others, but we cannot put a preference there. Yes?
Do you have a choose test model after they have?
No, it's the same generic model that is trained on both. Generic models have been trained on all types of images and videos from different positions with different types of field of views, RGB, IR, low res, high res, dashboard position, rear view mirror position, any type of position. That's why we call them generic, because we want them to work in their majority of situations. It will never be perfect for production. For production, we have to collect further data on these vehicles. Transfer learning will enable us to do that faster. Yes? Yes, yes, yes.
I might have missed some of the use cases with this, but are there law enforcement use cases in the future with this?
They keep crashing into
protecting people on their cell phones, or that their seatbelts aren't buckled, or solving the problem of infants left in car seats?
Yes, so there's the Hot Baby Act, Hot Car Act, 2017. It passed here in the US because of a certain number of deaths or babies left behind who passed away from extreme heat. There are all types of use cases. You mentioned like 3 or 4. Sure. Yes, all of that. All of the above.
So you're working with law enforcement?
We're not. We're not. If you mean law enforcement as far as like law enforcement that operates its own fleet, you mean, right?
No.
Like police and
I
stuff?
mean, the car is detected that somebody's been on their cell phone for the last 35 minutes.
Yeah, but that's data that doesn't leave the car today, so
Okay.
yeah. So all of that data is actually processed and it passed along to the vehicle's brain, which is the CAN bus typically, if there is one. And that data is not leaving the vehicle yet, unless there are other use cases. Yes?
So obviously it's focused on the vehicle, but do you also sell it, let's say, for medical use, maybe patient monitoring or something like that?
Could be. It's just not a strong pull. there from that industry. It's slow, there's a lot of red tape, you can't do anything unless it's HIPAA compliance, blah, blah, blah. It's tough. We've given the technology to a number of institutes, including locally here, Kaiser Permanente. It's not, it's a small market, maybe it's slow today, it's still in the exploratory phase.
But the software and the chip that you got.
Correct, that is correct, absolutely. So that's another use case you can add it to the list of earlier. That's another use case. Yeah, one last question? That's really immense. Yes, there is always stuff on our website. All right, thank you guys, it's been great, great questions.
Thank you very much, Modar. It was very interesting to have an in-depth glimpse into the future. So, we invite you to our next meeting, which will be at the end of February, and we'll post it in the Meetup group. Thank you very much.
Hi everyone. Thanks for coming for today's lecture. My name is Abhijit Thatte. I'm the Vice President of Artificial Intelligence and Software for AEye. We are a LiDAR combined with camera. We call it LiDAR startup based in Pleasanton, California. I would like to make this presentation interactive rather than just keeping all the questions at ease. So anytime you have any question or comment, just raise your hand. And before I start, what I would also like to do is, I'd like to kind of tune my messaging to the type of audience we have over here. So for people who have already been working with LiDARs or have worked with LiDARs, can you just raise your hand to give me an idea? Okay, we have quite a few. But there are a lot more people who have not worked with the technology. And for the rest of you, how many of you have worked with artificial intelligence, especially deep learning part of it? Please raise your hands. Okay, good. We have some sizable number of people over here. But there are quite a few people who have not worked with LiDARs as well as not worked with AI and computer vision or deep learning technologies. So I'm trying to dilute the messaging a little bit that this doesn't become like a completely archaic type of presentation where it becomes big and Latin. But again, if there is anything where you need more clarification, please just raise your hand. So what are some of the major perception tasks that you would expect or anybody would expect from a self-driving car? I just listed a few of those which are quite important ones. This is not in any way a completely exhaustive list, but just being able to understand what's in front of the car, other type of vehicles, people, animals, some type of road obstacles, maybe some debris on the road. That's what we call as object detection. Just identifying static objects is not going to be enough. Just the way when we are driving, we look at what's in front of us, we also look at what's around us, but we don't just stop there. Depending upon whether it's a slow-moving car or a fast-moving vehicle, we have the intuition in terms of where that vehicle is going to be next. Or if there are people on the road, adults versus kids, it's wired into us based on experience that adults typically would walk or move with a standard velocity. They're going to be more predictable. As opposed to if there are little kids around, they're quite unpredictable, full of energy. So we are tuned to thinking that this is a risky gap, we need to be extra careful when there are kids around. When the car needs to drive itself, it needs to have the same level of consciousness and make exactly the same type of decisions that we humans can do. And for that, being able to track those objects, being able to identify what they're doing, and also, in a way, try to forecast what they could possibly do next, which is motion forecasting, is also another activity that the self-learning car will do. As part of today's talk, what I would focus on is some of the highly effective architectures of deep neural network that have been published in public domain, how they have been using those, what are the different approaches that people have taken, what are some of the pros and cons, and are we there yet? Have we conquered the world, or is there more work to be done? The list that I will go through, it's a small list, it's by no means comprehensive, it's a very happening field, almost every week there are new papers being published. Just going to focus on 3 or 4 of those, which are some of the state of the art, they were published in the last few months of 2018. So before we actually get into the neural network architectures and their benefits, I just want to highlight a few things about what's the difference between the 3D data that comes from majority of the LiDARs versus the 2D data that you see from the regular camera. We are so used to the camera data, we get X and Y two-dimensional position in that. They have full color, they have very, very high density. Look at the cameras that even go on cell phones, like multiple megapixels. And if you are in the DSLR world, the camera has been selling for 52 megapixels and on. So extremely high density. As opposed to that, when you look at LiDAR, they have no color information. Their density, especially what you have from point clouds, is very, very low. It also tends to be non-uniform. But the main advantage that they have is in terms of the Z, or the depth information, and that also works very well in different types of lighting conditions or weather conditions. So if you are to look at both of these, for a self-driving car, it's not one versus the other. Both are going to be necessary. You do need the depth information. The car needs to be able to figure out what is around it in all type of lighting and weather conditions. So typically, the approach in the industry is to take information from both of these devices and do the sensor fusion and use that rich information. So as part of some of the architectures I showed initially, they will focus on using purely the LiDAR data itself. And then I'll talk about a couple of architectures that will focus on both LiDAR plus camera data fused into one.
So your
Yes.
company provides the cloud category intelligence to
Yes, so AI, our devices, we call them IDARs, it's intelligent detection and ranging. So we not only do the fusing of this data, but there's also another thing with the LiDAR that you provide certain scan patterns and it goes in the line scanning and it scans it accordingly. So what happens is when you look at the data, if you're taking data from the LiDAR, which really does not have the high resolution as that from the camera, typically you have to take a uniform scan resolution across the entire scene that you are looking at. You get that data, you get the data from your camera and you fuse it. What people realize after fusing that data is just the way if you have to look at our human perception system, when we look at something with our 2 eyes, even though we are looking at the entire scene, the specific point or the person that we are looking at, we see them in very high resolution. But everything around us is grasped in the low resolution by our eyes. That's the way our visual cortex and the whole system has been developed. We have a system inspired based on that. So we have some low-level embedded artificial intelligence where our camera and LiDAR works hand in hand. And that allows us to change the scan resolutions for specific objects or regions of interest so that objects, vehicles, people, any other otherwise, we can scan in high resolution versus everything else, which is typically the background, where it's scanned in low resolution. The main benefit of that is the data that comes in, the volume is much, much lower. Number 2, almost 80 to 90% of the data is about the things that the car cares about, so it's useful. And that translates into much higher frame rates of like 100 frames per second, or having much higher or longer range because we are able to conserve the energy for lasers and just use it specifically for specific areas. So a range up to like 1,000 meters or 1 kilometer So those are some of the benefits that our device provides out of the box.
Are you using spherical beam LiDAR, MEMS, or voice or something like that, or is it spun?
Ours is a completely solid state mesh with LiDAR. There's no spinning.
Variable index or refraction kinds of.
You said frame rate of your LiDAR is 100 LiDAR and camera.
For our LiDAR, we are able to get up to 100 frames. And it's primarily because of, our approach is different. We are not like, okay, let's just try to get as much data as possible and then process it later, which actually slows you down. Because there are only so many things you can do in a given period of time. We only focus on the areas that are of interest and do with high resolution. And plus, we are not continuously looking at 360 view. I mean, the way we compare our devices with ourselves, with humans, we have two eyes. We have a small part of our brain that does a pretty amazing job of perception. So, and we do it intelligently as biological systems. So we're trying to essentially model our systems inspired by our own intelligence.
So we use you frame that is set frame, and then you just scan each different area, and then we use a frame rate to finish this view, and then but that only focus on a certain area. Or the frame of the view just change all the time.
So because we have camera and LiDAR both combined together, both work hand in hand, we are able to get information from the camera to make some decisions about where to focus on, and we can command our LiDAR to specifically focus on where other view.
Right, so the frame and the view changes all the time.
Yeah.
So you 100 frame per second. That is for a fixed view or each whatever the scan pattern is.
It's completely software definable. We have multiple scan patterns, and they can also be defined by customers. They can go with a fixed field of view, but just focus on one part of the field of view, or they can even change the field of view a little bit if that's necessary. Those are the capabilities. Any other questions before we move on? So I'm just going to talk about specifically what LiDAR was and focus on some of the architecture. So if you just look at the LiDARs, as I mentioned earlier, the data is much sparse compared to visual cameras, very low resolution, and there is no color information. Now this creates a set of unique challenges for the deep neural network architectures. There's been tremendous progress if you look at say 2D perception in the last few years. In majority of the cases, if you look at like ImageNet competitions, the performance of humans was surpassed by majority of the DNMs like ResNets and ResNets even way back in like 2015. That's not still the case for the 3D world yet. We're still getting there. But there are a few approaches that people have tried over the last 2, 3, 4 years, and some of them have turned out to be quite fruitful, where people were able to surpass previous benchmarks and previous performances. I'll use 3 approaches that were most prominent and showcase also one example of each as part of some of the following slides. So one of the first approaches is instead of just using the 3D point cloud data as is, quantize that data into voxels and then apply 3D convolutions to that. So that's the first voxel-based approach, 3D point cloud going to 3D voxels to 3D CNNs. And one of the poster child examples for this approach, which really did a good performance, is what is called as VoxelNet. This actually came from Apple. There is another approach which is called as pixel-based. And the idea for pixel-based is primarily you have 3D point clouds, but you project your 3D into a 2D, like a bird's eye view, and then apply the two-dimensional traditional convolutional neural networks on that. The best example in terms of performance for that came from New York University, NYU. It was an architecture called, they call it complex zero. There is a third one. This one came from Uber quite recently. The paper was published around last year. So very interesting approach. This is not only for the object detection. This also does object tracking as well as motion forecasting on the network. So pretty powerful. And the approach that they took is, you can see it's almost a hybrid of both number one and number two. They convert 3D point cloud into voxels, then take 2D projection. There are some additional elements. We'll get into some of those details later. And they finally apply the 2D CNN. They call it fast and furious, and app name, you'll see why. And last, I'll showcase one of the approaches which uses both LiDAR data as well as the 2D camera data. And over there, the data gets fused. And here, it's again pixel-based approach, 3D point cloud to 2D point images, add 2D camera to the images, and then I use 2D CNNs. Yes.
So for the 3D point cloud, what are the performance benchmarks?
We'll get there. Hold on. I have slides with specific information. It's part of the question. We'll go through. For each one of those, you'll be able to see what's the.
Because it's very difficult for human to motion focus. Why not an information?
Important question. You'll get all the details. Any other before we get to next? All right. So just a quick overview of the voxel net architecture. Won't get into a lot of technical details. That's not the idea. A lot of you are not even familiar with DNS, but the way this works is it uses the raw point cloud as input. This is the architecture that came from Apple. And what this does is, this is the core part for feature learning network. What it does is initially it partitions the point cloud into individual areas that are called as voxels. The next one is, it takes that information, you can see the voxel partition, it's including random sampling. So what it does is, it uses this layer that they call as voxel feature encoding layer. They use multiple of those. Idea over there is extracting the information from individual points that are part of the voxels. So initially low-level features and then higher-level features, and so on and so forth. And once they reach a certain level, combine those up into 4-dimensional tensors and then feed it into that upward smoothing branch of convolutional middle layers that would aggregate those and finally use a regional proposal network to come up with 3D object proposals. And back to your question about the performance, it's the specific parameters of performance are in this table. It was Apple tested it on Kitty dataset, which is pretty standard for LiDAR or 3D type of data. And they have also done the comparison with some of the previous approaches. What I would draw your attention to is car, pedestrian, or cyclist, the top part where they have it. In that case, they're able to get to almost 90% roughly for some of the easy cases. Versus about like 78% for medium or low cases for cars. And for pedestrians, it's slightly lower, but compared to like some of the previous approaches, this was one of the highest performing networks when it was published. Again, be aware that this is a very fast moving space. So something that was state of the art last week could change in a week. Somebody else could come up with their own research paper and publish and completely blow away this benchmarks.
This is still classification.
So this is actual object detection that comes up with the entire bounding box around the car in 3D. So complete cube. But this one does not help you with object tracking as well as movement forecasting.
So what's the difference between table 1 and table 2?
So in case of table 1, what you are seeing is so what they have done is as part of doing the benchmarking, right? So in case of kitty data set, there are two types of ground truths available to you. You can look at the bird's eye view, which is a good prediction. You can also look at the underlying 3D data. And the first table specifically focuses on this bird's eye view detection, versus the second table which goes directly to the 3D detection. And the point that they were trying to show is, even though the performance is kind of similar in the same range, you still get, in almost all of the cases, you still get much better performance with bird's eye view. You know, like roughly 5 to 6 percentage points higher compared to 3D detection. And this is another interesting part. If you go across papers, you come across a lot of papers who do just benchmarking against one data set or one part of the data set, as opposed to running benchmarking against all that's available, running the ablation studies to understand like what part of the network is important, which part is not important. So I focused only on the papers that have tested their networks with and demonstrated rare. It's published, it's there, you can go and verify it. Come across papers where people would publish results, but there's no way for you to verify it whether it's true or not. So that's also one potential pitfall that you have to be aware of, that not all published papers are equal. You know, there are some that are really, really good, and you would know those when you look at those with the amount of rigor that they have put into their experimentation and providing the data. Yes.
So just like in computer vision, does this include object detection and classification at the same time?
Yes.
So the argument would have to say, hey, this here is the car, here is the
Yes,
desk.
exactly. And the only difference is that as opposed to, I mean, we are so used to 2D images, so with object detection we just see a bounding box. Because of the third dimension, but here you will actually see a cuboid. If I were to go to like previous image, it's not showing up here, maybe it will show some of the future images. Yeah. With actual cuboid, not just 2D bounding. So the next one, this came from New York University in NYU. This is called they call it complex YOLO architecture, and this is based on the famous YOLO architecture, which is quite prevalent in the 2D space. What they have done is also similar to previous network from Apple. They also have on input, and they do not convert it into voxels. You know, they directly apply the transformation to 2D bird's eye view, and then what they do is they're doing something interesting. Say here with LiDAR, you don't have any color information, so for 2D image, when they convert it to bird's eye view, they actually use the information like say the height or the intensity of the particular point or the density in a specific area as 3 channels, kind of like pseudo RGB for creating that 2D image in bird's eye view. And after that, just use the standard YOLO version 2 architecture on CNN. They also made a slightly different modification over there. There's something called the Vision Proposal Network. They have their own twist based on Euler's principle and using complex number in a specific way. And they're able to apply that and then take the predictions of those bounding boxes. And here the paper also shows that if you back project those onto a regular camera vision image for the same area, what those bounding boxes would look like with cuboids. And the actual numbers for this particular network are over here. And here you will see a comparison. I'll draw also your attention so you're asked question about the speed as to how fast it can work. In case of complex YOLO, especially for this table where this is based on that bird's eye view detection, complex YOLO is able to get up to 50.4 frames per second versus VoxelNet, we just saw in the previous slide, its speed is at about 4.3. And this is, again, not surprising, right? I mean, if you look at the mechanism in case of voxel net, they use the 3D point cloud, they applied the 3D convolutions, they're using 3 dimensions, versus here, there was a conversion from 3D to 2D and you applied 2 dimensions. So the computational complexity itself reduced from n cubed to n squared. And some of the benefits of that are showing up here. Now, I'm not saying that that's the only reason for the speed up, there are other things too. But this is typically what you would expect when you are able to simplify the computations without losing the rich representation of the device, data of the reality that we have from these.
So the three dimensions of the data that they are using, height, intensity, and density, it's not as uncorrelated as RGB image. If you think about a cuboid and the intensity and the point intensity and the density, they are somehow related. Are they using that mathematical structure somehow here?
So as part of that paper, they had done an ablation study and got some results in terms of which one of those is more important than the other.
You can do some inference, right?
Yeah. So I don't have those charts over here. You can just Google the paper, you'll get all the details. And they have some interesting conclusions over there. So what they found out in those areas is that height and let me put it this way. Intensity turned out to be more important for most of the objects, but not all the object types. Versus height was really not that important. Density was also okay. So those were their conclusions based on the study, but check the paper, you get much more insight. And the bottom table, similar to what we saw with the voxel net, this is directly about 3D object detection. But if you look at the performance numbers in terms of frames per second, they are very similar when compared to voxel net. Now, one thing you would notice is if you look at just the precision, complex yellow was not able to achieve the highest numbers, right? And they have shown it in majority of the cases. Some other type of network that has been able to achieve the highest numbers. But because having this type of very high frames per second rate, it's a strong contender to be there because you can get into this type of real-time decision making that is necessary if you wanted the self-driving car to drive much faster, more than 25 miles per hour. If you want to drive at 50 miles per hour or more than that, you're going to need these kind of frame rates and capability to process it. So that's why I included it. It's a good paper, really good in terms of the performance of speed. Sorry, I didn't get your question.
The criteria is percentage of object detected, right? So obviously it's not 100%, but in driving a car, you got to make it 100%. So what happens to these objects? Are there other sensors that you can help detect? So you have multiple sensors, clusters, so that your machine can eventually reach to 100%.
Okay, good question. Let me answer it in 2 parts. This particular metric, which is called as average precision, or sometimes you will see as mean average precision, the way it works is, you look at the object, and the detection is not that the object exists, but it also takes into account that how accurately you are able to define the boundary in 3D space, that cuboid. So you have an actual cuboid that, let's say, the person is standing here with the cuboid that is around the person, versus the network could detect the cuboid, and that cuboid may be a little bit off. So what you do is you look at the intersection of the cuboid and divide by the union of those two, and then you get these numbers. So if you have a perfect match, you would get 100%, but you rarely have a perfect match. You have your cuboids which are maybe slightly off, so the numbers start to go down. So not having a high number is not an indication that the object was missed. It's an indication that the detection and the intersection was not perfect. When it was there, but it was slightly off. But there are other metrics also in the paper where they will look at the traditional like precision and recall. So you want to look at recall for false negatives, you want to look at precision for false positives, and I will encourage you to go out and check those papers where you see the matrix, and you will notice that none of those are perfect. You know, there are like very high precision and very high recalls in many cases, but none of them have like 100%. So which means that there could be situations where these networks could miss. If there is an object, they could miss. If the recall is less than 100%, or if the precision is less than 100%, it means it may have some false detection. And that's why it could also indicate that it's quite possible that a single sensor may not be enough. You want to look at like multiple sensing technologies to make these systems foolproof. Good question. The last one in the LiDAR, before I go to the final one, which is LiDAR plus camera combined, this is called as Fast and Furious. This came from Uber, and they had essentially used a hybrid approach, both voxelization as well as taking the bird's eye view. But what they were able to do is something incredible. You know, rather than creating like say 3 different networks, one for detection, one for tracking, and yet another one for motion forecasting, they have the same network which has got like 3 prediction branches that do exactly the same thing at the same time. And because of that, the way they use the data set is also quite different. They don't just look at a single frame at any given time. They look at multiple frames over a period of time, kind of like a snap, a small snippet of a movie. That way they are able to understand how a particular object is moving, they are able to track it, as well as based upon its tracking and movement characteristics, they are able to forecast the motion for a few frames that are coming forward. And again, we won't get into detail. I would encourage you guys to look at this paper, but we'd like to just share some of the numbers that they were able to achieve. Pretty impressive for object detection, which is the top table, when it comes to the performance at different thresholds of intersection of aluminum, like 0.5 all the way to 0.9. And the time in which they are able to do all these 3 activities is 30 milliseconds, which is also pretty impressive in terms of like what they are able to achieve, like doing 3 things at exactly the same time. There is a tracking performance table at bottom, which is also giving quite good results. The only problem with this would be it would be very hard to replicate their results because they are not just using the KT data set. They found that the KT data set was pretty small for what they're trying to do. And of course, they're Uber, there are a lot of data of their own that they have collected from multiple cities in the US and Canada. And they mentioned that internal data set that they were able to use, which is probably 10 to 15 times larger than that of KT data set, and achieve this speed. So it would be pretty difficult if somebody is interested to do that just based on KT data set, because this is not just KT data. The last one I would like to talk about, this uses both LiDARs as well as visual cameras. And this is an architecture called as LEDCAM-NET, LiDAR Camera Network. Came from a university in Sweden close to Göteborg. And what they do is they use both the LiDAR data raw point clouds as well as the camera data as input. And it's very interesting. The architecture that they have used is very standard, what is called as fully convolutional network. It's the famous architecture for semantic segmentation in the 2D space. It's very common, nothing new. We just used it. But the variation that they applied was where to use that data. And there were 3 variations, which is the bottom table. Early fusion means all the data gets fused even before the single point gets fed into the entire fully convolutional network. In case of late fusion, the fusion happens just before the last layer, Remaining first 20 layers, there are separate channels for both camera data as well as the LiDAR data. And there is an interesting one which is at the bottom called cross fusion, where there are separate streams for both camera and LiDAR, but there is also fusion that happens in successive layers. And what you will see is, especially the performance data that they have provided, they are able to achieve this using that third scheme of that mixed fusion that happens across the entire length of the 3D population and network. And in this particular case, again, I know the numbers are quite impressive. The time is a little bit on the larger side, 150 milliseconds, as opposed to what we saw with some of the previous ones, like 30 milliseconds for Fast and Furious, or the complex YOLO, which was like about 50 frames per second, so amounts to roughly 20 milliseconds or so. But this is the one where they've been able to achieve impressive results. So these four, in my opinion, are pretty solid state-of-the-art architectures published in those areas in the last few months. This will happen in space. 3 months from now, there will be new candidates. 6 months from now, there will be something new. You can guarantee that. So now, what does this mean? Are we there yet? Right? This is the question that I always ask. Like, have we conquered, or have we finally cracked the issue? Now, one thing you always have to remember that all of these models, except for the Uber's model that we also use internal data, were built on Kitty dataset. Now, Kitty dataset has been standard, but it by no means is the most comprehensive dataset you can have. If you were to look at individual images or frames over there, a majority of those were collected in broad daylight in ideal conditions. We don't drive cars in ideal conditions all the time. Majority of the dark nights, fog, inclement weather. So that's where the data set has very few examples, which means that these networks that were trained and that were able to have a very good performance would be able to perform well in broad daylight, but it may not perform well in other conditions. And that's where the road will the road. You don't want to be in a situation where the network has learned with a certain part but cannot really work well. So that's why I personally think there is still more way to go. We will see more and more networks come up. Even better data sets than Kitty would get into public domain. That would be representative of all the weather conditions and driving conditions that we humans are usually subject to. And especially when we want to be able to drive at high speed, long range, high sensitivity, especially for LiDARs. Like if you're looking at very long range and there's a tone, say, tire about 700 meters from you or 2,000 feet from you, it's not directly visible. Visibility is pretty low, reflectivity is pretty low. So are the devices or sensors powerful enough to be able to see that and respond, actually report it back to your network so that the network can detect that there's a tire in the road. That's important. High frame rates, they are given, unless you have those, you won't be able to drive at this high speed. So there's a lot more work that still needs to be done. And as Ron was saying earlier, so it's still not at level 5, still like few years away. This is one of the reasons. This is not the only reason, but this is one of the reasons. So, thank you.
Thank you very much, Abhijit. It was very good to hear about this subject in depth, and also thank you for sharing everybody and having all these questions.
My pleasure.
Thank you.
If you have more questions, I can answer.
Thank you. Okay, our next speaker is Modar Alaoui from Eyeris. Very good speaker that I met in many cases, and also we've been working with Eyeris on some proof of concepts, so we became friends as well.
just wondering how you're going to monetize your technology. Are you going to license your perception stack?
I wish my VP of Business Development was here. We would have been able to answer that in much more detail and color than I can. There are multiple.
You mentioned that data source wasn't very perfect conditions. Is there any lack of data that's, do you not have a source for the data that you're linking in Sunnyvale?
So what I wanted to present was a way for anyone over here, if you wanted to go home and try some GPS that you can use, you would be limited to the public data set that are available. And what you will see, the majority of the papers that is published, they use the public data sets so that anyone can reproduce the results and verify the paper when they have done it actually works. So the main data set for that is KPX, and that one is limited. So as a company, AI, we don't have a problem, we have a lot of our own data, but that's not available to the public, so we don't really use
Yeah, can we start? Thanks everyone for sticking around. So my name is Modar, Alaoui, I'm founder and CEO of Eyeris. And I'll be covering what we do, which is what we call in-vehicle scene understanding AI. And that's particularly inside autonomous and highly automated vehicles. I can start with a few facts that most people are familiar with. Today, only about 1% of cars are shared. In 2030, about 30% of these vehicles will be shared, 25% of which will be autonomous. So there is no question that there is a major transformation that we are witnessing, which is primarily going from products-focused offerings to experience-centered offerings. So everything is going to be around experiences, not so much the product. The second fact is that once that happens, a number of things will happen, one of which is that the car will become the third living space. So it's not going to be the car anymore. It's going to be a third living space. It's a space where we spend more time, comfortably, safe. And that's going to happen at all levels, not just level 3 or 4 or 5, even level 2. And the third fact is, as cars become more and more autonomous, the focus shifts from driver to passengers, and then it will further shift from passengers to scene understanding. So car companies or automotive stakeholders will try to understand every single thing that's happening inside the car, because that is the a long-lasting thing that they're yearning for. And so to that end, a lot of companies are focused on driver monitoring, which is great, something we started with ourselves anyways 4 or 5 years ago. But there will be everybody will be witnessing a decline in driver monitoring as cars become more and more autonomous. It's just natural. And as we go into this golden era of mobility, which is autonomous, shared, electric, the most important things that car companies and businesses will care about is who's inside the car, how many, what gender, what age group, what emotions, what mood, what activities, what objects are around them, how far are they from each other, what's the other surface right next to them, etc. So all of that is combined in what we call in-vehicle scene understanding, or ISU. Lastly, the last fact is, this was a great talk, by the way. So synchronized vision will actually become important. So anybody that's doing any work on the exterior vision, whether it's with LiDAR or radar or a combination of both, are going to also look for more data. At the end of the day, this is a sensor fusion type of thing. So interior vision will become critical to optimizing safety and comfort. You'd probably want to have basically interior controls that respond accordingly when the car sees something on the outside. So, for example, the vehicle can brace for impact better or make the ride much more comfortable. And this is going to be essential for all levels of comfort. So what we've been doing for the last 5 years can be categorized into 3 things. Now we call it in-vehicle scene understanding. It wasn't a phrase, or it's not something that we coined back then. But we started with human behavior understanding. That covers occupant understanding, visual understanding. Everything is with camera-based, standard 2D camera-based. So visual behavior understanding is typically done through face and body language. Right? It's just as humans we understand each other is primarily through face and body language. Second component is object localization. This is actually not just localization, because obviously it's like the third step into the neural network, but it's detection, classification, and then localization within a vehicle. And lastly, surface classification, something we just announced earlier this month. It's a method using image segmentation that enables us to provide a class label to every single pixel that the camera sees in real time. And so the class label will be, for example, a dog, a seat, a chair, a footwell, a door panel, an armrest, a bag, a person, etc. So these are the 3 main components of what we do. If you look at the interior, it has 3 main things. There are people, and objects, and surfaces. Surfaces are typically things that are permanent in a car, just like what I mentioned. An armrest, a steering wheel, a pedal, a footwell, a door panel, etc., etc. So these are surfaces. And then objects, and then people. So we try to understand everything that's inside, and we do it with privacy in mind. It is embedded in the fabric of our core algorithms and an important part of our DNA. Everything that is processed, or everything the camera sees, is processed in real time without basically saving any images or videos. There's literally no capability of doing it anyways, because everything is processed on the edge with an AI chip. I'll talk about that here in a second. So there isn't enough space for even storing a bunch of videos or a bunch of images. And that's actually what explains the zeros and ones on the display, and also how it goes into each one of these categories. So there are some key components. We leverage multi-2D cameras inside the car. It could be 1 or 2 or 3. Ideally, one cannot cover everything, and that's why we use multiple 2D cameras. Any positioning, so 2D camera agnostic, whether it's RGB or IR or RGB-IR. Any positioning within a vehicle. Different vehicles have different environments, different sizes, different geometry. And so we accommodate all of that with further training. And then the second class, or the second group of technology components, is IrisNet. The IrisNet is a portfolio of deep neural networks. It's about 10 so far. 10 deep neural networks that run in parallel from multiple cameras at the same time, inferenced on the edge on a single AI chip. This was also an announcement we made earlier this year. And so that processing enables us to get real-time ISU, in-vehicle scene understanding, real-time ISU data analytics, in real time, right on the vehicle itself, right on the edge. So what enabled us to do all of this over the years is really, it's a major challenge for deep learning and AI, and especially computer vision, is you cannot train an algorithm unless you have a good amount of data. And there was no data initially when we started. So we had to collect our own data sets. Over the last 5 years at our lab in San Jose. And this data was collected from about 3,200 individuals today that we hire for 1 hour at a session at a time. They come in for driving simulations at one of the vehicles, and also we take them on a predefined route in San Jose. And we collect a lot of data, of course with their permission, they get compensated. So we collected the largest in-cabin data sets, over 10 million images and videos to date from face analytics, and that's how we started. We started actually with emotion AI. And then we extended everything into body tracking, activity, object, and lately surface classification. The Eyeris net portfolio of DNNs, I mentioned earlier, comprises of 3 main categories. One is HBU, or human behavior understanding, and that's from face, body, and activity. Object localization, we provide a class, size, and position, as well as surface classification, where we give a pixel map of the interior cabin. Surface contours, we can tell you what's the shape of the armrest or steering wheel or the seat, and what's the shape, but also what is the contour from which we can derive the shape. We deploy everything from mobile nets all the way to res nets. Depending on the accuracy requirements of the customer, we have to go as deep as 50 layers, I think, is one of our deepest network. Front passenger seat, footwell, etc. Class, size of the object, not size of the bounding box, but actual volume of the object, the contours of the object. It helps provide higher level of accuracy when it comes to prediction of what the object is. And it serves as, you can see here in blue, as a secondary analysis and validation. So that's kind of really an overview of the architecture. Of course, for surfaces, I mentioned earlier, we provide the pixel map, contour, region, and class of all surfaces inside the car. So this is kind of a organized way of showing what the deliverables, or the snippets of what the deliverables are today. Body analytics, face, activity, and object. Whatever object we train for. You have a question?
Yeah. Can you describe your stack where it's happening? Because you said inferencing at edge, but is it all the things not on the edge?
Everything is on the edge. I covered that with the AI chip slide. Everything is on the edge. Nothing leaves the car.
To train the system to recognize moving the permanent features, seats that tilt, headrests go up and down.
Yep, all of that, absolutely. Those are still considered surfaces with variations. So things that are going to be always stationary in a car, not leaving the vehicle, and they're different positions. Absolutely. There's a question here. I have a couple of slides about that, and I'll promise I'll convince you. So, just like you know, every car company today, or company in the automotive industry today, does exterior perception. And generally, that is done with either cameras alone, or cameras plus LiDAR, or cameras plus LiDAR plus sonar plus radar, etc., for the purpose of trying to make sure that the vehicle understands or perceives the world similar to how we can see it here. Perception, right? So that method for the longest time, the last, I don't know, decade, maybe not quite, has been called image segmentation. And it's been the de facto standard of how cars see, or maybe robots inside a shopping center or some sort of indoor location, or whatever the case it is. But it's always been the de facto standard, and there's literally nothing that can challenge that today. What we're working on is 2D cameras only. And we came up with our own image segmentation. So somebody earlier I heard mention semantic segmentation. There are a few other methods. Panoptic is another one. Instance is another one. So it enables us to do basically background and foreground. And we believe, or we're trying to work hard on making it the de facto standard for interior vision, right? You may ask, what are the other methods? Well, typically I may say, just put in a bounding box in the body or an object to identify what these things are. But that's not enough for an overall understanding. So this interior image segmentation, I mentioned briefly earlier, it enables us to classify or put a class label on each pixel. So if we're working with a standard 2 megapixel camera, just off the shelf USB webcam that you can buy for $20, generally that gives you about 2 million pixels, right? So we take each one of these pixels and give them a class label. Group of pixels belong to the dog because of the shape and the texture, etc. A group of pixels belong to the floor, to the human, to the backpack, to the bottle of water, etc., etc. So when we run the algorithm on the chip at about 15 frames per second, we provide information about 31 million pixels per second to customers. So on every second, we give you 31 million information, right? If we're using one camera, we do 5 cameras, which is kind of what our demo cars have. That's about 155 million pixels per second at 15 frames per second. We don't necessarily have to go that high as far as the frame rate, but for production, typically about 5 frames per second is plenty. Yes?
A question, you have a dog and a passenger there. What if the dog is sitting on the passenger's lap? Can you
Absolutely.
detect, segment, and differentiate?
Absolutely. So the idea is to do detection, classification, localization, separation of different things. And that's the purpose of the segmentation. I can actually tell you how many pixels the dog is away from the passenger's lap, or how far my elbow is from the armrest, so that you can activate certain intelligence features from the vehicle. Maybe the armrest can move up a little bit so I can sit comfortably. This is an example. That's the idea of image segmentation. Yes?
Do you do, or you plan to do any pre-processing on the cameras?
No, we can, but we're going to have to, these cameras are going to end up being costly. So basically what your question is, Mobileye, a company that most of us know, they do pre-processing right on the camera because the chip sits in the back of the camera, but it's not necessarily deep learning, or at least at first it wasn't. These chips were cheap, $10 processors, whereas an AI chip would actually be much more expensive. But that's distributed, so you can have each camera basically do the processing on its own. But then if you want to combine the information from multiple cameras inside the car, because one camera cannot see everything, then you're going to have all of that information pulled into some sort of central decision-making engine. And you're still going to need another processor to do those rule-based decisions, basically. So the beauty of an automotive-grade AI chip is that you can inference 10 neural networks in parallel from up to 6 cameras at the same time and still do that at a high frame rate or close to real time. So we announced earlier at CES basically the introduction of a production-ready computer vision ASIC, that's application-specific chip optimized for our DNNs, which is already automotive grade AECQ100, grade 2, so that's just temperature. Grade 1 basically goes all the way up to 125 Celsius. Grade 2 is enough for the interior. Actually, if anything goes up to 120 or 105 Celsius, the whole car is in trouble. So grade 2 is enough for now. It is also ASIL QM. For those of you who are familiar with safety standards, there are ASIL A, B, and C, etc. For the interior cabin, QM is enough for most OEMs, for most car companies. For some, maybe Japanese or other types of OEMs, they may require an ASIL B, which basically means the chip needs to kind of go through a much more rigorous type of testing that can withstand harsher environments. It also has to do with redundancy and failure and things like that. So the chip does up to 10 trillion operations per second. That's 10 teraops of throughput, which is plenty to run all of the neural networks on 6 cameras inside the car. And it does all of that while consuming just under 7 watts. Under 7 watts. So a typical GPU uses about 30 watts. Some of them use 15 watts. There is actually some settings in Jetson Xavier that can use up only 15 watts, but then it is also at the expense of performance, and that's still high. So in a future where cars are all going to be electric, remember how we were just 10 years ago when we received our first iPhones or just smartphones. These devices were initially measured by how long the battery lasts, to the point where Samsung spent about $5 billion in the first 2 years after Apple launched iPhone just to say our battery lasts longer. So that becomes basically the only metric really that people care about. You also heard of range anxiety for those of you who drive electric vehicle. So when you're targeting a traditional industry with a brand new solution, while that industry is actually going through a transition, kind of makes it even more difficult. So power consumption is of the utmost importance to all of them, literally by the 10th of the watts. So you don't want to put something in there that can drain the car's battery faster, and therefore the consumer, that's about the only thing that consumer will remember really. So power consumption is extremely important. Just for those of you who are not super familiar with AI chips, there are about 50 companies today doing this stuff. It's hard. I think there are about 3 to 4 that came out with something at the AI Edge Summit. I think in October was the first time all of these companies actually were put together here in Mountain View. And about 3 of them had something out, something operational and working. Some of them have raised over 150 million and they still didn't have anything to show for. It's a hard problem. And what matters basically at the end is throughput versus power versus cost versus size. These are the main things. We could probably narrow it down to throughput and power. So anything out there that does about 10 teraops today consumes close to 100 watts, and that's basically NVIDIA GPU. So it's we're gonna see, it's interesting times. We're gonna see how these this will turn out in the automotive industry with by saving a lot of power, and that's kind of what everyone unanimously has been asking for. The other advantage is that it can power up to 6 cameras. So 6 cameras in a car. I don't think you necessarily need the 6 cameras in typical sedan. But certainly for like a third row seater, maybe like a large SUV or a minivan or some sort of bus or whatever, large vehicle, you kind of want to cover every single square inch of the car to understand what's happening, especially if that vehicle is actually serviced for that particular application, meaning it has the intention of driving autonomously at some time, and it's going to need to pick up people from location to location, and it needs to know or to make sure that the vehicle is always clean, empty of trash, empty of forgotten objects left behind, and things like that. People are seated where they're supposed to sit, proper posture or whatever. So all of that becomes basically important, and we're literally just at the beginning of this user experience. Just the chip. But pardon me? It's at peak consumption, turning all the clocks on the chip, connecting all 6 MIPI interface cameras, running all 10 DNNs, no more than 7. I guess your next natural question would be under what temperature, and so typically we can lose about 10% of the power when it's super cold, or it can consume up more, actually the other way around. It can consume up to 10% more when it's hot, or and then the other way around when it's cold. So basically the tests have been done with extreme temperatures, and that's actually part of the automotive grade, is that you have to test it and certify it for different temperatures. The 105 Celsius I mentioned earlier is actually in Celsius. So 7 watts at up to 105 Celsius, and all the way down to -40 Celsius. And that's what makes it, one of the reasons that makes it automotive grade. A lot of questions, go ahead.
A car is one of the worst investment as a personal investment. It only use 5 to 7% of the time, and otherwise it sits there.
Okay.
It also is one of the least efficient asset in terms of all the land it occupies and sits there.
Okay.
Now, moving on, by 2030, the predictions are with self-driving car and all the issues like there will be fewer cars, not more cars.
That's arguable, but keep going.
So I have data and I have...
Good, great. What's your question, please?
The question is, why are you investing such big amounts in all these chips? It may never give you any return.
Yeah. Well, just because the customers actually want them. It's not like we're investing, they want them, so we have to.
Your chips, and you're making billions of dollars worth of investment.
That could be necessarily true. You're saying there won't be any cars in the future?
Literally. By 2030, in the US,
Yeah.
with very, civilized driving and with all the things, there will be fewer cars.
Okay.
Plus the aging population. So that's where...
That's actually when the cars will increase, because they will actually mobilize all the aging population.
There will be fewer garage, there will be fewer service stations, and there will be fewer car.
I'm sure you have a lot of background and study. So we are customer centric, and so should every company, startup or large, customer centric, meaning we develop only when the market needs something. We can prepare for it for however many years. We prepare and offer something that the market needs today. And so this is some of the stuff that will be shipped in 2021 by the exact volume that the customer wants. So that's kind of my answer, I guess, to you. But let me go on. I have a lot of other slides. Yes?
A related one. So who's your customer and what are they looking for?
Car companies and tier ones, OEMs and tier ones, and they're looking for in-vehicle scene understanding analytics inferenced on something that doesn't consume a lot of power, while it's very powerful, so that it can also do some of their other sensors like a radar or other things on the inside of the car. Okay?
Have you analyzed that if you network misidentified objects? So basically, you're in automotive industry and the safety, even though you're able to do that, there's still safety implication here. So what happens if the DNA misidentified
Great question. So that applies to everything, not just an object. Even if we say that person seems to be angry, whereas actually that's their resting face, they're not angry, they just have some sort of something there. So the answer is that applies to everything. We provide data analytics to car companies to fuse with other sensors, make sense whether that data we give them is actually accurate or not, depending on the context, and then they decide on what to do as far as reactive support systems. So they decide to basically put a lot of weight on vision. So let's take the Eyeris data, we'll give it about 80% accuracy at any given time, but then let's further analyze or further do some sort of validation with other sensors. We have radar that can also give us some sort of heart rates monitoring probably, or respiration, also some sort of body volume. We can still do it today with blind radars. And any type of analytics that we give them, they have to put in, you know, kind of this decision-making engine through complex sensor fusion algorithms and then they decide on what to do with it.
So do they have certain criteria to meet yourself? You say, okay, I have collected 10-minute data set. I'm just going to use this 10-minute data set, test my chip, and make sure I pass 80%.
Well, the benchmark is higher than that, than 80%. Typically, we try to be at over 97% for everything that we provide. And that is hyper customized on a per vehicle, per model basis, depending on the camera, resolution, type of camera, location of the camera, field of view, and maybe like 20 other things. Go ahead.
Yeah, there's a question about the chip. So you said it's got over 700 pins.
716.
Yeah, I would guess most part is I/O, I guess.
Yeah, I/O is the board. So the chip is the most important thing. This is Silicon Valley. Every other company out there builds silicon. So boards are boards. You can make one fairly inexpensively today with some sort of NRE fee of 30, 25K. And some of them will actually go to customers depending on the I/O they require. For example, if they need MIPI interfaces, only 3 of them, not 6, to save up on something, then that board will accommodate accordingly. It's not a big deal.
Yeah, so I guess my question, why would you need that many I/Os?
It's the customer that needs whatever I/Os they need. So, for example, they may not need HDMI and Ethernet and yeah. So the I/O will be customizable to the customer unless there is, you know, some generic boards that are inexpensive because they're produced in large volumes that multiple customers can just use. I don't have to use every single thing that's every single input or output that's in that board. Yeah.
Quickly, what's your approach on memory? Do you have local cache and external RAM, or everything's on die?
So both. We have local memory and external memory that will sit on the board.
And what process
now? May not comment on that. I can't comment on that.
What's the process feature size for the chip you're using?
Process feature size. It depends on the neural network. Sizes depend on each neural network that we run. I think this was public, so I can't get around it. So we announced it was a 10 nanometer process. You can only expect the next gen to be a smaller one. And actually, what's in production is 7 nanometers today. So I think that's it about this chip. Oh, there's one more slide about it. Gen 1 is, so Gen 2 basically will have a 7 nanometer chip. There's this, what we call an Iris chip accelerator software IP, something that runs our neural networks at a much faster pace. And that's something that we plan on integrating in Gen 2. A lot of use cases, your question earlier. Safety is at the baseline of everything that we do. It has to be. It's almost like the Maslow's pyramid, right? If you don't have air and you don't feel comfortable, or if you don't have air and food and water, then you can't even survive. And so as humans, natively, we cannot be, we can't be comfortable, I guess, if there is no safety. Then comfort features come secondary. A lot of times there's some bleeding over between the two. Convenience is another set of features. And then lastly, services. This will primarily be enabled by data. Data generated from the analytics. And that data could be used by companies outside of the car, mobility as a service providers, Walmart or Starbucks or Amazon or Netflix or anyone that may want to use that data in order to customize the offering on the inside of the vehicle. Frankly, we haven't figured out that part yet. First batch of vehicles will potentially start leaving the plants in the end of 21 and potentially at the beginning of 22, and then we'll see what that will look like. So there's a value proposition here, just kind of a summary. I'm down to my last 3 slides and I can take more questions. We've built the largest data sets. That's being native. We had to, we didn't have a choice, so sure, we can brag about it. We do ISU, so in-vehicle scene understanding, not driver monitoring system only. We have a unique set of neural networks. We announced the proprietary AEye chip. We do worlds-only interior image segmentation and worlds-only 2D body tracking. Something we announced or we did at CES 2018, and we're still leading in that space. Multi-2D cameras, commercially ready today, and so we use multiple interdependent IP blocks that kind of beef up the algorithm. So this is kind of a snippet of some of the analytics we provide. This is on the website. From anything interior pixel map to surface ID to number of occupants and presence and body pose and body contour and location and head pose and age and gender and emotions. It's just all the work we've been doing over the last 5 years. But most importantly, this is what car companies or mobility as a service companies would actually use the data for. So anything from changing smart displays to intuitive 3D touch, lower body bolsters. For those of you who are familiar, there are actually some bolsters to cover the feet in case of an accident because only the upper parts can be covered by the airbag, but there is generally a lot of damage to the lower parts. So if they know the position, the size, and the orientation, how the person is seated, then they can deploy these things intelligently. Customized air quality, adaptive speed, personalized media. The car will be the new center of media, there's no question about it. Separator airbags in crashes, people actually, a lot of the injuries happen when the passengers clash into each other, unfortunately. So separator airbags would be phenomenal if we understand where is each person at any given time and how far down to the pixel level. So, and this is a list that most of it is provided by our customers, really. Roadmap, I mentioned 7 nanometer. There will be a cloud exchange API just to enable companies to probably access this type of data. Finger and hand tracking and understanding all the way to fingertips. There will be a scene reconstruction that we're kind of tampering with right now. Transfer learning is a big one. We do want to reduce the size of training from one vehicle model to another. Right now we have to go through all the layers. Later on we just want to work on the last layers and further train so that can give us a lot of scalability. And lastly, we're working on what we call fleet of data. We have plans to collect about 2 billion images within the next year or so from 5 vehicles that will be basically running 2 hours each every day. Each vehicle will be equipped with 5 cameras. Each camera is doing 30 frames per second. And so it comes up to approximately 1.9 billion images. as far as data sets. And that will be with variant number of people and ages and gender and positions of different cars and different camera positions, etc. Large market opportunity. I don't think I'll have to convince you about this. There's some market trends, right? So computer vision actually will reach about 17 billion by 2023. And driver monitoring systems will reach about 10 billion by the same year. There's a lot of announcements as far as driver monitoring system. It's phenomenal, it's fantastic. I actually like it. About 5 years ago, we were preaching or talking about, hey, you need to put a camera in front of the driver, and now we don't have to do it anymore. OEMs are convinced. And as a matter of fact, there are a lot of companies that are focused on this DMS, maybe 5, 6 more. Problem is, it's a single camera and it's focused on typically eye tracking and head pose, which are 2 analytics among about 100 that we offer. And so these are car companies that made announcements for the next couple of years. And this is my last slide. So in summary, there is a transformational shift from product focus to experience focus. So what will matter when all the cars will look the same and the technology works perfectly and every car can take you from point A to point B flawlessly, what would matter is how that experience on the inside of the car has been, right? And so you can only understand that experience if you have more visibility on what's happening on the inside. And we're working on this opportunity to become the de facto standard for in-cabin vision with ISU. We believe we have a unique technology and ahead of the industry, validated and commercially available today. I can take the rest of your questions. Go ahead.
If you look at the FPGA, how much power do you get?
It depends on which FPGA works, where we can combine all of these neural networks into only 3 later on with further training, etc. But then, why bother? So an AI chip can give you an additional 10 teraops just by sparsification, right? FPGAs are great for something else. Plus they're reprogrammable, so that's great. Yes?
Do you consider somebody like Guardian Optical Technologies like a similar market, similar?
Yeah, potentially. I think if they're using cameras, why not? Anybody that's using a camera on the inside of the car is looking at the same market. Actually, that's great. It's fantastic. That means more people are thinking the same way, and more people are pushing for more safety, as long as it's anonymized, right? Or non-personally identifiable information. Yeah.
I was going to ask if you might draw some distinctions between them and yourself, if you're familiar with what they're offering.
I'm not super familiar, so we're multi-camera, and there was a slide about all the value proposition that we offer. I'm not super familiar about what it is that they do, other than they operate on the inside of the cabin, I think, with both a radar and a LiDAR, so that's great. I think good complementary. Vision has to be the primary source of information. Even as humans, we spend about 80% of our brain processes, 80% of the information that the brain processes is actually vision, so it's very, very rich, it's two-dimensional. So vision has to be the primary thing. There are complementary things like radar, data, and other, anything else. But the more the better, honestly, for the industry as a whole. It just makes it a healthy marketplace. Yeah.
So you're able to, through the pixel, know where, let's say, a hand is, fingertips are?
Yes.
So would you be able to translate that to like mouse motions or any type of?
Correct. Gesture is what you mean? Yeah, activity is a kind of gesture. Yes. Yes. To a certain degree, without depth as of yet, unless if we gather information from 2 2D cameras, then we can calculate the disparity map, and then we can do depth, but your question is correct.
Okay, so why don't you just use NVIDIA chip instead of?
We worked with NVIDIA for, 5 years. It's not us who decide, it's the customer. Power consumption and price and form factor, and the fact that they're alone at this, I guess, all are non-desirable things. Yeah. Next question. Go ahead.
I guess this kind of human behavior and gesture detection,
Yeah.
this might be useful in a lot of other fields other than car, right? Like VR devices, TVs, that they want to detect your.
Okay.
Are you planning on smart things like that?
Yeah, the automotive industry is a huge industry with a small number of players, and typically it takes a long time before you can crack it, and we're so knees down into that for now. I guess the other industries would be retail, social robotics are kind of not a low-hanging fruit, but just somewhere there. Automotive is probably the lowest one, plus that's where we spend the most time. But retail, security in general, surveillance, and especially that retail is transforming now, like with Amazon Go and all of these companies doing cashierless checkout. Definitely retail, security, airports and shopping centers and things like that, and then I would add to it social robotics when they mature up some more. Yes?
Okay, so looks like your list of HBU and OL are like two lists.
Yeah.
Understanding develops when you kind of analyze the relationship between human and object.
The only relationship is when we need to understand activity. Other than that, the human behavior doesn't necessarily have to have any relationship with an object unless you're trying to derive an activity, such as speaking on a microphone. If you see a microphone, you identify it as an object, then you see basically my lips move and I'm speaking, then you can say the person is speaking. It's on a temporal basis. Drinking, for example, if you have the wrists close to the mouth, without seeing the object, you're going to say person eating / drinking. You have no idea. Unless you can analyze other things, but if you see the object basically as a bottle of water or a sandwich, you can say, or a cup of coffee, you can say eating or drinking with a higher level of confidence. It's just an additional layer of accuracy.
You are not out there, the OEMs will take care of it. You're just providing analytics descriptively.
Well, part of the analytics is the activity too, so we can say eating or drinking if we see both the motion of eating and the object, an apple or whatever, or drinking if it's a bottle of water. And then, again, they can always add additional analytics on top of that from other sensors. Yes?
I would assume that in the car, another type of information is sound.
Yeah, very good, audio.
Yeah, okay. So do you guys also think or already support kind of augmenting these kind of information?
Yes, so it's natural for us when we provide or when you generate some algorithms, we deliver them in some form of SDK with a set of APIs, and it's for that purpose, for anybody to use any additional data from any other sensor. If you think of sound, it's just another sensor, right? Data to integrate, certainly. What's interesting actually in audio, and we're talking to a lot of folks about futuristic audio deployments in cars, is this directional audio, right? And so it's directional means it can only play what I want, and so the person, the passenger right next to me will not hear a single thing, although my audio is at, I don't know, 25 or, you know, at almost max. And what enables them to do this is a number of things, of course, audio related, but the other thing is vision, because they need to track where the ears are together at any given time and at what position. And so the challenge with that is, we did some tests and some work with one of the leading audio companies, is they cannot settle on anything less than 60 frames per second. Because if you're moving your head, if you just do a no gesture, that audio needs to follow you very, very quickly. And so at 60 frames per second, I mean, you're gonna need more AI chips, right? Whereas the typical car companies require only about 5 frames per second for production. So that's kind of been a challenge, but I know there are ways to mitigate. Good question.
Another thing
technical question. Could you please talk about, if publicly available, about your core team and your production plans? You mentioned 2021 with your customers.
So that's what we expect, end of 21, so don't take it, maybe 22, that's typical with automotive guys. It's going to be high-end, as it is the case with any new feature in a car. Even electric windows and windshield wipers initially started in a high-end vehicle, right? Most high-end vehicles are actually in Europe, so you could draw the conclusions there. So at the beginning, it's the customer that will have to pay for such features, obviously, as it is the case with everything else. So there will be like a, I don't know, an additional $1,500 package that does this, and that, including cameras that can potentially make your ride safer until there is good enough volume, and then that becomes standard in everyday cars.
And your core team is in San Jose?
Everybody's in Palo Alto and San Jose. We don't have one. We don't have one yet. Certainly would have to be competitive, but we don't have one yet. It depends on volume and commitments, on how many years, and a lot of things, but we'll have to be competitive. So driver monitoring system, there is a price range there that's kind of known, so we're going to try to be around it, just to be competitive. Yeah?
Another technical question. Are you running a network in reduced precision?
With what?
Reduce the precision, shorter resolution,
Yes and no, it all depends which network and what's desired. Reduced precision, reduced resolution even, right? So we don't process everything at HD, we don't have to.